Okay. Sorry, it makes me laugh. Okay, good. It seems that is the okay. We're gonna start in just a minute, and we really appreciate your patience.
I'm really sorry. Deeply sorry once again. We had
Tu peux bouger par là pour voir? Okay, I have to revert the video.
the room that we had reserved was we had problems of connection, so we tried to change the room, and so we had another room assigned, but there are some people in the room, so we had to move and find a room on the spot, and so unfortunately we have one, but we had to handle some network problems also. J'ai des slides, est-ce que je partage mes slides ou pas? Je vais pas les utiliser, enfin c'est juste pour
No, no,
avoir
no.
des références.
Just go ahead on the board. Let's not waste more time.
Okay. So hello everybody, c'est en ligne sur YouTube là pas?
Yes.
Okay, hello everybody, so I'm very happy to be here today. I'll be presenting Active Inference for the 4th seminar of PMMC2. I will be using the following references. Active Inference on discrete spaces. And synthesis. So there's several authors. So D'Acosta, Lancelot D'Acosta, Thomas Parr, Noor Sajib, Sébastien Vezelik, Victorita Neoxu, and Carl Friston. So in the Journal of Mathematical Psychology, 2020. Second reference is Active Inference as a model of agency. So Paul D'Acosta, Samuel Tenka, Dominique Zhao, and Noor Sajid. 2024, that's a preprint. And a third reference that I don't have, that is not public, but I will ask the person who wrote it. So it was one of our interns that we supervised with David and I. So David and I, which is Rida Lali. So he did a master report. So I will ask him if I can share it, because I think it's nice, nicely written. And Rida Lali. So this is in 2021. Yeah. Okay, and it was about active inference and emotional inference, and linked the PCM. So inference active. Pour les agents émotionnels au sein du modèle projectif.
In English.
So active inference for emotional agents inside of the PCM, projective consciousness model. Okay. So mostly I will use let's say the first article as a reference. And the good point about this report is trying to link the tables of notation with respect to the explicit expression of the distributions. So the table that I will use is table 2 in this article. It's like one of the tables that have all the different notations and all the correspondence between what the variables are and their notations is in table 2. But today I will try to make it like use make everything explicit so that there's less possible notations, but there will still be notations, and I will change a bit the notation with respect to the articles, but we can discuss the link with what is in the article. So the aim is just to make explicit what is a variable, what depends on what depends on time, what doesn't, so that we can have a very like direct, I hope, direct idea by seeing the formula exactly what is changing, what is fixed, and what corresponds to what inside of the generative model. And then the second article is a generalization. So the first one focuses on the naive Bayes as during when you do variational inference, and the second one is a bit in a more general, let's say, setting. But in any case, so the second one is let's say a way to say that you can encapsulate the active inference in the way that is formalized in the first article inside of a more general setting. So we'll play with both ways of seeing it. So I will start now with the first presentation, which is a presentation that is a bit general about what active inference is. What I mean by general, I mean the two big parts of active inference, which is first inference with respect to some observations, and then how to choose actions by specifying the less possible, like without putting too many focus on exactly the shape of the generative model, or to be more precise, the shape of the distribution that you use to approximate the generative model, and explain if we were able to compute explicitly the posterior, what the active inference algorithm would be doing. And then I will go into the details by explaining what variational inference is, going into the details of exactly the way active inference is specified inside of the first article. So don't hesitate to cut me if I make mistakes or if things that I say are not clear. Okay. So we need to specify first the generative model. So I will go first I will try to, like in 20 minutes, present exactly active inference, let's say, giving some details, precise details, but not at the same time, not too much. And so we'll assume that first we know about what the generative model is. I will give little explanation about it, but very little. And then I will go back to it so that we can, if we have questions, be more try to spend more time explaining what generative models are, what is variational inference. Okay, so a generative model is basically a collection of hidden variables that corresponds to, so here depending on T, that corresponds to variables that are used to describe an environment, but you cannot observe. So it's the way that you assume that you have information about you assume that the environment evolves in some way, but you cannot have access to all the information about the environment. Or let's say you have to model the way it evolves. You're not sure about how it evolves, but at least you have to suppose you have a model of how it evolves. And you have some observations that also depend on time, which you can make. It means that you have some variables that allow to explain the environment, but you have access to the dynamical system with respect to how the environment changes only through some observations. So I'm not precising for the moment, I'm not going into details of what a PMMC is, but then I will go into more of this detail now, later. So here, S is a random variable. It's in fact a collection of random variables indexed by time, each taking a value inside of a certain space, ES. For example, we can assume that this space is finite, so it takes value this random variable inside of a finite space, and that they can be all equal. So I will associate to the random variable S1, S2, S1 up to T, a space of possible configuration that I will note like this. Similarly, observations, the random variable of observations, corresponds to the collections of random observations, taking values inside of a space, which is for example, a finite space. And I will denote the space of configurations like this. And similarly, the space of the joint configurations will be denoted as O1, O2. So the way that you relate hidden states and observations is through a map that is stochastic. That associates to a certain observation at time t. So this is an element of E. Let's say if they're all equal, ES, and here EO. So that is a random variable. This notation is random variable. This is the state space associated to it. And an observation will be with lowercase notations like this. So I take an observation and it's related to a state at time t of the hidden variable. So this is simply saying for a given state, I can make an observation with a certain probability. So how to define what? So the notation fs simply means I have a function that relates states to probabilistic observations, and I put a little index s to say that it's related to sensory information. Okay. So f of s has the property that if you sum over all the observations in ET, in EO, this has to be equal to 1. A particularity about how active inference is, and the specificity of active inference in the first article that was in the previous board is that we will assume that this function depends on a variable, but that will denote z, it's denoted a inside of the article. That corresponds to, depending on the value of z, then the observation can change. For example, for things that we studied about curiosity, it could be through rotations. If you rotate, then your kernel changes the way that you observe. If you rotate and you have a finite vision, visual field, then when you rotate, you're going to have the relation between your hidden space, the state's hidden state, and so the value of the hidden variable with respect to its observation that changes because you change your sensor. So for the moment, we'll say that z is also itself a random variable, and the random variable we will denote it big Z. Now, why this notation? So the notation Z is just to refer to a standard notation or some notation that you find for PMMCs that corresponds to a kernel that associates to a hidden state a probability distribution over the observations. So it's just to conform to the classical notations for PMMCs, for, let's say, stochastic optimal control, of relating hidden states to observation. But for us, it's a little z, because the way you relate it is also changing, and it lives inside of a space that we can denote as easy. In the article of the first article about active inference that in the references, the little z lives in a space where it is all the possible kernels, so functions that associate hidden spaces, hidden values, sorry, values of hidden variables to a probability distribution over observations. So the whole space of kernels that we will call this a kernel that goes from one that associates one state to a probability distribution over observation is the space even. But we will go into these details later on. Okay. So now we just define what the variables are. Hidden states and observations. Now we will define a way to relate the variables, to make them random variables. In other words, to define a probability distribution that has to depend on theta, on the states, sorry, on O, on the states, on Z, and I'm leaving some space because we also have something more that appears, which corresponds to actions. So we will assume that we also have different actions from the agents corresponds to different probability distribution over the observations, the hidden spaces, hidden states, and the Z that encodes the way that you observe from a hidden state. And so the notation I will put for the actions. So is little pi. And little pi is in fact itself a collection of actions up to time t. And they live inside of the space big A. Okay, now we have everything to define the generative model. So the probability distribution. So this is the generative model. The joint probability distribution is what we will call the generative model. So the joint distribution P that I will note with a double bar, meaning that it's fixed for once. So we choose one generative model, and in the way that I will describe active inference, I will assume that the generative model doesn't evolve. I know there's a way to make it change with respect to observation, but to simplify, we will just focus on inference and action and not changing the generative model. We consider a generative model, one the probability distribution over the observations, over the hidden space, over the hidden variables, sorry, the states of the hidden variables. Tac, tac. Over the kernel that corresponds to the observations, and over actions. That is equal to F big pi, depending on the choice of policy that you make. So this is the policy. So I didn't say the pi corresponds to the set of possible actions that you can do. I will call it, now change the notation, and we'll call it policy. And keep the big pi for all the possible policies that you can make. So now, pi that you find in the literature of active inference, I will replace it by policy. The associated random variable is big pi. That's why you have the quantity that depends on pi on the policy here. And in fact, it is a collection of actions. So one policy is a collection of actions. F of Z, let's see. So this is the generative model that I consider. So something that is interesting, at least that is hidden in this notation. So several things. Each of these terms is a probability distribution. So I will take P for calling the space of all probability distributions. Each one is a distribution, probability distribution, over the space of configuration of each of the variables. So the good thing here is that I index the variables on the functions that I define. So it allows to, instead of putting P everywhere, I'm saying I choose a probability distribution that is written like this. So that in fact, this is simply the probability of the policy. But I want to make the distinction so that when I talk about the marginal distributions, which we'll call later, I will put an explicit notation. So for here, I'm just saying I want to find a way to show how I want to find an expression of how the variables interact between each other. So I put the terms for each variables, and then I put terms that allow to make the variables interact between each other. So here, this lives in P of EV. This lives, so it associates to ZT. In fact, it associates to S in big S, probability on S. And this is what,
個等黑板嚟。
Hello?
yes?
No, this was a mistake.
And so here it associates to S in S, Z in big Z, the distribution over P. Okay, so here I put it just once. Yes. And this is in big. Okay, so what did I want to say more? So if you fix a way of observing, and if you fix a policy, forget about these terms, you're just specifying a transition from a hidden state at time t to a hidden state at time t plus 1 that we can denote as st2 st plus 1. So here I put t. Okay, it depends on what the policy that you chose. Maybe like this t transition that depends on the policy, and then you have observations. With here a kernel fs that depends on z. S here means sensations. Okay, it's not a variable. So maybe I'll just realize it now. I will put it upstairs so that we cannot confuse it with a variable. FC, FNC. And this does this way of saying how you move from state time t to state at time t plus 1 and how you observe doesn't depend on time. So if I go to the next step for a given policy, but the policy depends on time, but because it's a collection of actions, but I suppose that I fix the policy. That shows the policy. Then you have this graphical representation of the factorization given for the generative model. So now there's something that I hid is that here you have a little toe, and here you have a big T. So I will now explain what is little t, big T, and little toe. So you have questions with respect to now.
Anybody has a question in the?
And I'm going, I mean, for the people who know, I'm going very slowly, but it's, I mean,
No, no question.
Okay. So in the previous equation, we had a little toe, a big T, and we assume that little toe is slower than big T. So what are we doing? We start with state S0. We go to observation O0. Here we have f of s that depends on the source of T, a transition T that depends on the policy, S1, up to S little toe, O toe. It means that we allow to make observation up to time T. But now we want to have it to be able to make a generative model of what will happen in the future. So imagine that you arrive, you did observation until now, which is time tau, and you have a full, complete memory of what happened before. You know that the observations corresponds to a change of your environment, but this happened in the past. Now you're at time tau, and you want to be able to predict what will happen in the future, but you don't have observations for what will happen in the future. So you just complete with the same transition. Up to the end, SFT, but you don't have observations. So this is the generative model that I wrote in the previous slides in graphical notation. When you assume that the observation kernel Z is fixed, and you chose a policy, which should be called, but the policy corresponds to a collection of actions. And in general, the way that it's written, again, the way that what it corresponds to doing is choosing.
C'est pas super cette couleur pour le.
Mais il en faut une autre alors.
Non, mais c'est pas grave, c'est bien gras.
Okay. So here, instead of considering that the transition depends on all the possible actions that you can do up to time t, you assume that each transition depends on the action that you're doing at time where you're doing this transition. And so here you have a tau, and then the last one you'll have a t-1. Okay, so now I finished about introducing the generative model. Now we will talk about inference, which is the first step of active inference. So active inference is an algorithm that allows to generate algorithms that outputs behaviors or collections of actions in for a certain agent. So active inference is an algorithm that outputs behaviors of an agent. And the idea is that this behavior corresponds to an adaptive behavior with respect to an environment. So the aim is not to solve the task like you would find in a stochastic optimal control, to be optimal with respect to your task, but just to give a generative model of behavior. And here the generative model is not this one, but it's the whole algorithm. Okay. So now we go to the first part of active inference, which corresponds to inference. So let us assume that we're at step I equals 0 of the active inference algorithm. I equals 0. So we have a generative model as input. Let's see. I will rather say that we are at step time. Oh, sorry. So we did total iteration of the active inference algorithm. What we have always is a generative model. And we have a prior distributions on the policy the time. And a collection of observations, O, of one up to tau minus one, and a new observation, O tau. So this is the input that we have. So our aim now is to compute the probability of S1 up to T, Z, all with respect to observations O1 up to O2. So we are given a collection of observation until time tau. We have our generative model. So what we can do is update our distribution on the hidden variables, which corresponds to variable of states. Hidden variable corresponds to the hidden state of the environment. One hidden variable is also the way that what we use to observe and relate states of the environment to real observations, and the policies, which corresponds to the actions of the agent, up to a certain point, which is our horizon, big T. So tau, always lower than big T. Okay. So this is the first step. Of the active inference algorithm. What I mean by this, it's computing the posterior given observations. This is posterior. Okay, but this is difficult to do, and this is known to be difficult. So most of the time, what I mean by difficult, I mean computationally costly, sometimes intractable. So instead, what we do is we approximate the posterior. So doing so is called variational inference. I mean, there are several ways of doing it, but one way of doing it is through what is called variational inference. Which we will detail after finishing presenting the algorithm. So morally, we're going to replace Q, replace P by a distribution that we will call Q. That will depend on S1 to point T, Z, and the policy. You can choose a lot of possible factorization or a lot of possible approximations. So it's just a way that we say we want to approximate the posterior, and we approximate it through a simpler distribution. And the approximation is through variational inference, and variational inference corresponds to minimizing free energy. So this is the first step of active inference.
So just Grégoire, the brown chalk doesn't render very good.
So I'm going to go get one chalk on the other side.
Yeah, because I'm afraid that given how dirty the blackboard is, it's difficult to see whatever Grégoire writes with the brown chalk. So Grégoire just left for a minute, looking for another color. Do you have, meanwhile, among the people present, any comment? No. So just a little bit more patience. As you can tell, we are very low tech. Yeah, not super well organized, but that's also the French charm of our approach.
Is it readable? That's only the thing.
Yeah, the white is readable, but try to replace the brown with the pink.
So let's try with
this one.
So we will replace P by a similar distribution, but just simpler.
No, that's better.
And we will give it okay. It's okay.
It's better.
So I will just use white.
Yeah, white is better. And
so now we saw the first step of active inference, and we related it to free energy, but not explicitly. We'll go into the details after, but it is through variational inference, and variational inference corresponds to minimizing free energy. So we will spend the full 30 minutes on variational inference after. So now I'll talk about the second step, which is how do you choose actions? So a key point in this setting is to choose we introduce a probabilistic version of preferences. And let's say, to make it simple, with respect to the state of the agent at a time as t, with t bigger than tau, but lower than big T. So depends on z normally, but let's make it simple now. So this is a probability distribution over E. So we want to encode preferences, but preferences in fact correspond in a Bayesian, like if you want to take a probabilistic point of view, corresponds to states where I would like to be more, so states that would be more probable with respect to my actions, where I would states that I want to be more appearing because they correspond to a greater reward or something like this. So instead of encoding the reward explicitly as a function of the state, you encode it probabilistically. And you introduce a second, say, free energy. So the second this time over the policy that you choose. That accounts for a term that is an exploitation term for P of S at time T Z knowing a given policy, so with pi equals pol, that relates to D in a way that we'll explain later. Plus, so this is related to achieving preferences.
C'est pas grave, non, mais c'est pas grave.
Comment tu fais?
IE.
I.
E.
And a second term that is an exploration term over the same distribution. So here I introduced a new notation, which is big P and the random variable indexed on P. What do you mean by this? And of course, condition 2, the observations. So here implicitly, you always have the observations. Condition 5. And the observations, O of Q1T equals your set of observations. Similarly here. So what I mean by P, S, T, Z, condition to pi equals the policy tau 1 over tau. So it's the marginal distribution. Marginal distribution of P that we had before, condition to P for the policy and the observations. So what we computed at the first step over the variables, so for the variables, for S at time little t, so this is a random variable, and for Z. So I have a collection of variables which I'm not interested in, so which corresponds to the variables S1 up to T minus 1, S T plus 1 up to T. And I just simply take them away. Not interested in them. I sum over them. Okay. So I mean, if you have, this is simply summing all the things that I don't want to look into, and then just this is the definition of the marginal distribution with respect to a random variable. So with respect to one variable that you want to look. So it depends on how you say it. You can say marginalize over, so over meaning for this variable, but what you mean is that you marginalize by summing on the variables that you want to consider. So now I take this part because I just explained what it was. And the way you choose your action, so you update your prior on the policy as taking something like exponential minus f2 of your policy, and your action at time t is the one that maximizes over the policies. So is the maximum over the policies that equal to A0 up to AT. Let's say this is var changing. So once again, it's just confusing one stuff here. You sum over all the A T TL in the space of actions, the sum of Q of the policies, but you sum only the policies that are A, let's say 0, A, T. This one is fixed to be A, T, up to A, like T on this one. And then you get a new action, and then you loop back. So there are different variations of how you choose Q policy. You can also add a term which corresponds to choosing actions that are consistent with the inference that you did at the first time, at the first step. But here I'm precisely following in active inference on discrete state space. So what I just remarked is the remark little 4 with respect to equation 10. And now, morally, we finished presenting active inference. We didn't present the specific of what Q we are choosing, nor why this relates to free energy, because we did not explicit what was the exploitation term, nor the exploration term. And it's what we're going to do now. And so to do this, we need to introduce what variational inference is, because you do not compute explicitly this quantity. You compute an approximation, Q, that is easier to compute. So this has to be replaced by the Q that we saw before. So do you have questions here? Is it clear, unclear? So maybe here in the audience, do you have...
For me, it's very clear. Thank you.
Okay, Jules? Okay. Not too slow, not too fast.
No, the only problem I can see is that the blackboard is so dirty that the contrast between what you write and the background is sometimes a bit, but that's more kind of a technical issue for our audience online.
No, it's okay. Sorry once again for the bad quality. We need to find a consistent manner of getting good quality.
Yeah. Alors, but otherwise I find it very clear.
Okay, so if
Personally.
nobody has questions, I will spend some time. So now I can assume that we presented what active inference was, and I can repair two equations which gives explicitly what is the term of exploitation. So it's equation 10 in the first reference. So this equation 10 of active inference on discrete state space. So for the ones who want to stop here and say, okay, now I got the idea, I understand how to use this. You don't go to equation 10 to have an explicit expression, and then you also have a way to an implementation of active inference. And I hope that the presentation helps you see a bit more how active inference works. This is the aim of the seminar. Okay, So now we'll have to discuss what is variational inference if we want to understand more precisely the first step of inference, first step of active inference, how approximating P by a simple distribution.
Dans la mesure où tu peux, essayer de laisser le moins possible de marques blanches, tu vois, quand tu es sur le tableau. All right. Yes.
Okay. But now, variational inference. So it's the second part of the presentation, variational inference, and then we'll wrap everything to get the explicit expression of active inference. So assume that you have two variables, x, a random variable, taking value in x, and you have y, another variable, taking value in dy. And you have a joint distribution, P, x, y, that depends on x and y. You observe y, and you want to compute P, x, condition on y, x, y. So the Bayes rule, so basically if you make an observation, the best guess that you can make on the rest of the variable given this observation is what is called the conditional expectation, conditional probability, and you compute it through Bayes rule, which is P of x on y, x, y, is equal to the joint distribution over the marginal distribution so the ones who know, the problem is computing this quantity. Because it's a sum over x in the x of P x, y, x, y. But now imagine that x is in fact a collection of binary variables. So each one takes values in 0, 1. Then the sum here is a sum that has 2 power n terms. It's huge. You cannot compute it. So you would like to do posterior, but if you have too many hidden variables, you can't compute it. So how do you compute it? You can use dynamic programming. For example, a very famous example is filtering for hidden Markov models. I will not go into the detail. I could, but I think it's not relevant now. There's another example, which is if you have a graphical model. So a way to factor the interactions of your variable through, let's say, a way to capture the interactions of your variables through a factorization of your probability distribution. You can sometime do dynamic programming to have the exact expression of this posterior. So if you have an acyclic graphical model on X, you can compute this quantity in much less operation than 2 power n. And so it's tractable to compute the posterior. Most of the time, you do as if you could compute it exactly, but you can't. And you can use the similar algorithms. Of course, I'm thinking about the belief propagation. But all what is hidden behind all these different dynamic programming algorithms for HMM, so filtering, for graphical models, belief propagation, what is hidden is, in fact, maximizing a certain entropy under constraints for a class of distribution living in a space that is lower than all the possible distributions. And this is a remarkable fact that we will see now. But I always mistake the signs, and I don't want to feel like mistaking the signs on the blackboard. So I have my notes, so that is good. So now this is number minus log p. We try to improvise, and I don't not improvise, but so basically in my notes I go to I use energies, but okay. So we will do it like just so we call that the entropy of a certain distribution that lives at the x is, if you take the physical convention, it's q of x, there's a minus, q of x, or x in the x. So there's a minus here, it's important. Okay. Free energy with respect, so variation of free energy with respect to a quantity q is simply the expectation with respect to q. So I suppose that the temperature is equal to kT equals 1. So it's the expectation with respect to a certain energy function. Minus the entropy of qx. That is free energy. It's called Gibbs free energy. So there's a relation between the joint distribution and the energy function that you can put here. So what is an energy function? It's just a function that goes from Ex into R that is measurable. But for us, the energy function H will be equal to minus the log of the joint distribution. So H of X is minus the log of P X Y, little x, little y. But here I don't put y because I fixed y to be given by the observation. So the remarkable fact about free energy. So little comments first. But no, also the remarkable fact, and then so the remarkable facts about free energy. Is that if you maximize overall the possible distribution over P of X, the expectation of Q H minus S of Q with H here equals, like we said, minus log of P x y. Then the one that maximizes this is exactly the posterior, P of x, knowing y. And second remarkable fact, the maximum of this. So here it's, of course, the minimum. Sorry, minimum, because I'm thinking about maximizing entropy, but here's the minimum. So the minimum of this is equal to the log minus the log of the sum of exponential minus h of x. It's an ex. And now if you replace it, this is where I was afraid to make this sign mistake. Exponential, so log p, so minus log ln of the distribution p y of y.
Ton écran.
So small parentheses, this is in fact equivalent to maximizing the entropy of Q of x under the constraint that the expectation over Q of x of h equals a certain value u to define. And the reason is because this is just the Legendre transform of the entropy. Basically, you're introducing the constraint through Lagrange multipliers, and then you just need to tune the Lagrange multiplier to make the coefficient be in front of the Lagrange multiplier, should be a lambda, related to the observation that you do. This is a small parenthesis. Thing that is interesting now. So if I decide just to optimize over a family of distributions where theta is included inside of P of x, then I know that this will always be bigger than minus log P y y. So the idea of variational inference is to say, so first, why is this simpler to solve? It's not that it's simpler to solve, it's that here you don't have to compute the marginal over py. If you optimize this, you would get it when you optimize over all the simplest. So you replace a computation on the sums which take 2 power n computations, and you replace it by an optimization problem. And so, for example, we could do gradient descent and say, oh, I am satisfied with reaching this point, and then I can stop there. So it means, in other words, you replace something where you have to do all the computation until the end to get the value or an answer. 2, I want to optimize something, and I am okay to make a mistake of up to epsilon that I can even sometimes control. So here you transform the problem of computing explicitly a sum to a problem of waiting enough time for the convergence of a gradient descent, for example. So you switch the perspective. In the first term, when you do the sum, the only moment where you know that you got something that makes sense is when you did all the sum. Here, you can do a gradient descent and have some criterion to stop before. So that's the first reason, transforming this problem into an optimization problem. The second reason is because sometimes if you choose theta good enough, Gaussian, for example, then it's extremely simple to solve. You know how to solve explicitly and analytically. So you don't get exactly the posterior, but something that can be close enough to it. Or at least something that makes sense in terms of you can represent your posterior as being Gaussian, for example, if you assume that Q is Gaussian. As if instead of computing the posterior, you were projecting it on the distribution of Gaussian variables, projecting it in a way, and then you get a Gaussian equivalent of P, of the marginal distribution, which you couldn't do before, only by computing. So this is exactly what we will do now for the last step, when we present the inference step of active inference. In active inference, what you do. So by the way, this is very closely related to the Kullback-Leiber divergence. So if you want to write this explicitly, you see that this is the sum over Q XX log, so the relative entropy, Q XX, big X, over, and here instead of plotting a distribution, we put the joint distribution XY. So this is related to the Kullback-Leibler divergence of relative entropy. Both mean the same thing. But the difference with the Kullback-Leibler divergence or relative entropy is that you should put a reference measure that is a measure. Here, you have a joint distribution. This doesn't marginalize to 1 when you sum on X. That's why I say it's related, but it's not exactly the same thing. Because if you were to minimize the Kullback-Leibler relative entropy, you would have to find 0 here. And the reason is because if you take this the other way around, then now you have exactly the Kullback-Leibler with respect to the posterior. Kullback-Leibler divergence. Now, the first step of active inference is choosing a very particular Q. So in active inference, the first step, so this now we'll call free energy F of Q. First step of active inference. The inference step. Is choosing the Q to be so important notations. So recall that we have the variables that are our variables X are S1T, Z, I. So now Q, what you want to approximate the posterior by, Q S1 up to T, D, the policy is equal to Q dV, so probability distribution on the possible observation kernels that you have, Q over the policies, and then the product of K equals 1 up to T, Q, K, S, K, pol. So now if you take in the free energy P X Y to be P S 1 up to T Z I So this is x and y to the O1 up to tau. Right? Minimizing this quantity over the theta, that is all the q that can be written like this, is exactly the first step of active inference. And so you can do it by gradient descent, and you can express it by simplify. So you can, what you can do, and it's a nice remark, is that you can do the max over the first one, so z, then over the pi, and then you get all the max for this term, depending on the policy pi, and so we can break it into 3 optimization problems. Okay. So do you have questions here?
Anybody online wants to ask a question at this point? Nope. If you do, perhaps I think there are those little icons where you can raise your hand, but you can also be much more spontaneous and just start talking. We like that, and interrupt, so do not hesitate.
Okay. So now if everything is good, then it's the last part of the talk, which is we will say exactly what is the exploitation and the exploration term, taking into account that this is our approximation of the posterior distribution. So we said that Q sorry, so I'm confused because there's a lot of chalk. So we said that this is the approximation of E tau, where tau now recall. So for the second step of active inference, we chose the distribution D that is associated to preferences. And the exploitation term, so sorry, D is a distribution over ES. So at one time, so depending, this is not all these states, but one state. It can depend also on the time, but to simplify, we assume that it's just at some time t, we want the agent to reach its desired state times E Z, which corresponds to the configurations of the observation curve. So the exploitation term is the Kullback-Leibler divergence, so DKL, I will recall the expression after. I mean, I talked about it before, but I will write it explicitly. Q over ST, so the marginal distribution of Q, which you can compute easily because the factorization that we had before in Q allows it to do it, but here it's just the marginal distribution in ST. Z, knowing the policy pole, with respect to the, we'll put it here, ST, Z. So it is simply the sum over st in st in s. I assume that z is finite here, which I know it's not finite, but let's say that you can only assume that you have a finite collection of observation kernels. In active inference, you put the distribution on all the possible kernels that can appear, then you get an integral, but I don't want to put an integral, so I just assume that I choose certain observation kernels that make sense, and finite number. So I take z in degree z, q of xt, the known policy, st z, ln of q, st z known policy, st z over the st z, st z. So this is the exploration term. So this replaces the same term that we had for P, but it's easier to compute. And this is what drives your behavior because it's what you want to reach. So the relative entropy or Kullback-Leibler divergence, I said distance because it can act like a distance. It's not really a distance, but it acts like a distance, which is basically that it gets smaller when you get closer to what you desire. So if this gets, it's a way to say when this term is close to this term. So you put this as, you could put the L2 norm, for example. You put this as a way to say, I want to enforce that my approximate posterior marginalized over these quantities, which corresponds to the state of the imagined environment at time t. So t bigger than tau, lower than big T. So big T, the horizon, with respect to the state that I want to reach. And then you have a second term, which is the exploration term. And for us in what we studied a lot, can relate to a curiosity, even if it's not exactly the same. It's not exactly the same expression, but you could, instead of putting the term that I will present now, put epistemic value. It would make sense also, at least I believe. So the second term which is exploration, doesn't depend on the preferences. It is the expectation with respect to Q, ST, Z, knowing your policy, I equals Paul, log of F, S, O at time T, one observation, state T and Z. Okay, but here I cheated because there is missing something. And I want to just detail what is missing. If we go back to our P1DP, X1, X2, X tau, XT, XT, O1, O2, O tau, and observation stop. So in your generative model, you know that you make observation up to time tau, but not further. Here, you have a term with respect to observation at time t. And here, this doesn't depend on the observation, or at least you're just computing the state of xt, an approximation of the state of xt, knowing previous observation. So a way to account for possible observation in your generative model is simply to add one possible observation, fs, at this time, that relates to possible observations at time t. So you simulate, the agent simulates what happens at time t, and simulates possible observations. And now, what you put here. So just 1 second. Yeah. So before put this way. And so here I need to multiply by f of s. Now something that depends on OT. And I put the kernel, which is OT, condition on ST, and Z. So now I will erase this. That's just a way for me to relate XT and possible observations. And here, the expectation is with respect to a function, not to a value. So here, I need to take these two away. Or I can say, with respect to the associated random variable, OT, ST, Z. So this, in other words, is just a sum. So if this, I write it as Q, ST, Z, OT, I. This term is just summing over all possible value of little st, little z, little ot, q of st, z, ot, knowing the policy. So here I put st, z, ot, knowing pol, logarithm of f of s, ot, st, z. And then we finish our presentation.
Thank you very much.
Okay.
Okay. I have questions, but they would be mostly confused and confusing, and I don't want to waste anybody's time since we have a bunch of folks here that knows that stuff very well, and other maybe that do not know it as well, but that are kind enough to be online with us. Would anybody want to make comment or discuss? For instance, Carl, you are here. We are lucky to have you. Do you want to make a few points, or do you have any things to add or perspective to give?
Ah, yeah.
Yeah.
I can see myself. No, a marvelous presentation. And it does look very beautiful on Zoom, because the dirty whiteboard looks as though it's been silvered. It's very, very artistic. The one this is a very erudite and formal and impressive exposition of stuff that I know and love. The one thing that I thought was interesting that I hadn't heard before, and I thought was just worthwhile foregrounding, is in the derivation of the variational approach and the utility of variational free energy, the reference to maximizing entropy under constraints and the appeal to this is what you would have got if you put Lagrange multipliers in. I thought that was very clever. Not only is it clever, but it also shows formally a duality or an intimate relationship between James's maximum entropy principle under constraint, or a constrained maximum entropy principle, and the free energy principle as applied here. And there are certain people, say like Dalton and Stony Brook, who would say that the free energy principle is just dual to the constrained maximum entropy principle, and certainly from looked at through the eyes of a physicist, that's absolutely true. In that James was trying to elaborate a generic physics of observation or measurement, which of course we would read as inference, but it's all the same thing. So I thought that was very nice. If you could write that down explicitly and in terms of Lagrange multipliers and just talk about constraints, I thought that was a very useful perspective. And then from the Jaynes or Maxent perspective, what is the generative model? It's just a way of specifying your constraints on this kind of thing that is conforming to the maximum entropy principle as observed, or the constraints on your inference or measurement are specified by the generative model. So I thought that was very nice.
Yeah, I agree that it's like this is why like all the different perspective of entropy are like so most of the time sometimes we get the question like why do you choose entropy as a quantity to distinguish like to find the distance between probability measures. And I think that one of the reasons is that it gives you, let's say, very good, let's say, family of distributions that make sense statistically. And then you can find it for exponential families, but you can also, like for people who look at information geometry, you can find like, let's say, some equivalent results, but stated differently. So I agree that it, like entropy is like, it's not just a distance. Like there's many reasons that there's a work of Shensov also that related to invariance with respect to how you relabel your observations and kind of an invariant with respect to your observations. And the fact to say that everybody like fell on this concept, which is entropy and inference related to entropy and like even EM algorithm that you can rewrite as maximizing the left entropy and then the right entropy and then the left entropy until it's consistent, which makes me think about a lot in the way that you active inference maximizes the left entropy and then the right entropy, but for, and then let's say the free energy, right free, like, so the right Kullback-Leibler divergence. I know that there's one more term with exploration, but then you do it with respect to some actions, so you don't specify every distribution that you had at the beginning. And so you see that this kind of for very like good family of distributions, exponential, for example, a lot of different inference, a lot of different, let's say, way to do inferences are equivalent to just maximizing some kind of entropy. And yeah, this is remarkable. But it's very nice is also that you, so there's this, and then there's also the fact that when you go on this on other family of distribution, you kind of lose all this like possibility to have different perspective on it, and then they kind of split into something different. But then at the same time for HMM and acyclic graphical models, I still conserve this possibility to, I mean, it's very intriguing. I don't know, I mean, it's
No, but that's very good. And Carl, when exactly Grégoire was making that relationship with this entropy maximization under constraint, that's what you would call it, and it's the Legendre or Lagrange multiplier? It's Legendre. Lagrange, Legendre transform and Lagrange multiplier. Sorry about my ignorance. I remember once, I think it was during a seminar organized by Maxwell, that you discussed that. You know, the entropy maximization under constraint, and I knew that when Grégoire would be relating that explicitly, you would like it. So I'm not surprised of your comment, and I'm happy with it.
There are some fields that worked on algebra, like when you look at exponential families, and I think he specified exactly this. Like for exponential families, this way of seeing entropy and seeing it as a convex optimization problem under constraint and getting free energy. And it's one of the rare places. I mean, there are other places, but where there's an explicit scheme of how to maximize entropy over linear constraints. And I think there's chains also, but like most of the time they say you get critical points and then it's explicit, but it's not explicit because you still need to find the good constraints. And then Stomfels does this. And if you look in the things that I wrote a bit, and Olivier Peltre and Daniel Penquin on for graphical models, if you get an interpretation of belief propagation, you see that it's exactly simply maximizing the sort of entropy, a kind of entropy, combinatorial, with some combinatorial terms associated to inclusion and exclusion formula. And then you just look at the critical points. So you get exactly the family of distribution that you're expecting, but then you want to exactly fix the Lagrange multiplier. And then you realize that belief propagation is just a way to find the right Lagrange multiplier with respect to the constraint. And so you fall back to something like a gradient flow, in fact, which is basically you have like you're changing your problem. It's a problem on your Lagrange multipliers, and you're just trying to minimize them, and then you do gradient descent. But if you do it discretely in a way, you refine belief propagation. So but there are some families for which families of distribution for which it doesn't work. But
so maybe you could make I mean, I know you're making a note on this and emphasize in your note that aspect of the relationship that you put forth here. Thank you.
So I work on the
yeah.
gradient flow and the expression. I worked with once you cite, we started working on it with. I mean, so there's already a lot of things that exist, and the thing is, try to find, to be sure it's completely new. This is like the difficult part, but we worked a bit on it with Marc Lambert, just to cite him because we worked on it, and in the end, maybe we'll just to cite him.
Yeah, so Grégoire has a very high standard, and he doesn't like to write things that are not really new. So it's
No, it's just
Well, yeah, but they were new to some people, so I don't think that would rule that.
yeah. Any other things you would like to add or discuss? Grégoire?
Well, I will just one more thing, if I may. So Grégoire mentioned information theory. Now, although it may not be new, I think the link between interpreting variational inference and in particular the Bayesian mechanics that attends the variational free energy principle, it would be nice if you could say, if we just start with a constrained maximum entropy perspective of the kind that Jaynes would have used, we can also link that formally to the information geometry. So, and as you point out, that information geometry really does rest specifically on a KL divergence, and of course Jaynes would like that because he was really focusing on entropy as opposed to sort of other Basher-Stein measures or measures of distances, and I think the information geometric interpretation, the maths I think is the same, but the interpretation I think provides a very useful perspective on what you could call Bayesian belief updating. You mentioned belief propagation there, as a particular case of Bayesian belief updating. And of course, one can see that as movement on a statistical manifold that is equipped with a metric that has a geometry. And of course, that metric is, can now be expressed as a path integral of infinitesimally small KL divergences. So, I think there's again a really nice conceptual link between that all rests upon relative entropies or KL divergences between a sort of maximum entropy view of physics and a more inference belief updating dynamical process where you're moving on a statistical manifold whose very existence depends upon a metric that is the relative entropy that underwrites the Jaynesian perspective. So again, I'm not sure that I think that would be new. I think to sort of write about Jaynes and information geometry in the spirit of all the Japanese scholars, for example, I think that would be a very new thing.
Thank you very much.
Oh, and maybe that could be an opportunity of collaboration with you, Carl. As has been a little while, we have not done things explicitly together. But anyway,
I'm getting too old to remember all the maths now. You can suggest me as a reviewer, a friendly reviewer.
Yeah. Thank you very much for the remark. I will definitely. This is. I mean, it would be a nice to make a paper that is allows to simply have a global perspective on all these different points of view. I would be very happy to write something this because I find very, very nice in fact too.
Okay.
It's always difficult to write something and you think you won't. I mean, you want to write it, but then you never know if you. I mean, in the end, we have to get things published, and it's how it works. So
yeah,
it's good to know that this kind of papers, which are more like trying to get an overview and all the different perspective in a way that is very like I think it's good to have it.
Exactly, didactic,
didactic,
and at the same time,
it's nice to see that this is
interesting. Not everything has to be a breakthrough, but sometimes connections that people have not thought about that afterward become obvious when you help people to realize them. This is also kind of a source of great epistemic joy. Oh, I did not see that. Oh, yeah, that's right, and that's good also. That's part of No, anyway.
Cool.
Okay, so nobody else wants to talk or say something? Okay, so then thanks everybody, and sorry for the complexities of our setups and the fact that we were late, and we'll keep you posted for the next session as usual. And so then see you next time, and thank you very much, Grégoire, again for, as usual, your great work.
Thank you very much, all of you.
Okay, goodbye.